1, 2, 1, 2, 1, 2. One, two, one, hello, hello. 1, 2, 1, 2. Alrighty. Hello, good evening. Sorry about the interruption in the stream. There was a issue that came up with the microphone, but we should all be good now. All right, so let's see. So let's recap a little bit. Today we're going to wrap up chapter 4 and chapter 5. No, sorry. We're going to wrap up chapter 4 and we're going to start chapter 5. Is what's going down. And to do that, we have we have a few topics to go over in chapter 4. Oops, hang on, sorry. There we go. Okay. So we've got a couple topics left that we need to cover in chapter 4. I'm gonna put these on just so I can keep tabs on how things sound. All right, so we finished talking about VSEPR theory. All right, and VSEPR. So just by way of recap, Lewis structures tell us something about connectivity. And bonds. All right, VSEPR theory, which is VSEPR, tells us about three-dimensional shape. In other words, molecular geometry, and bond angles. All right, that's what VSEPR theory talks about. And so that's kind of the whole picture on structure, our investigation of molecular structure and all that stuff. Right, correct. I'll go back and fix the date after the stream. So we have so after Lewis theory, after VSEPR theory, we're going to talk about intermolecular forces and the types of intermolecular attraction. And to do that, first we need to talk about something called an intermolecular. Well, we need to talk about a periodic trend known as electronegativity. All right, before we can talk about intermolecular attraction, we have to talk about something called electronegativity. All right. Now, electronegativity is a measurement. It is a measure of how much an atom wants more electrons. All right, electronegativity is a measurement of how much an individual atom wants more electrons. And as it turns out, electronegativity trends along the periodic table. So it changes in a predictable pattern as you move through the periodic table. So as you move from the left of the periodic table to the right, electronegativity increases. So the further to the left something is, the less electronegative it is. The further to the right something is, the more electronegative it is. It also increases as you move from the bottom to the top. So the closer to the bottom an element is, the less electronegative it is. The closer to the top an element is, the more electronegative it is. All right? And like I said, the measurement, because electronegativity is a measurement, you can look up these values. That measurement determines how badly an element wants electrons. The higher the number, the more an element wants electrons. All right, so the higher, oh, hang on, I can hear my 2-year-old. Hang on one sec. Sorry about that. My 2-year-old found his way into the office and outsmarted my brother. Uncle's on babysitting duty, and he found his way in. So, anyways, I apologize for the breakup in lecture. So, electronegativity is a measure of how bad an atom wants an electron, and the higher the electronegativity number, the greater the atom's pull. On, should say, electrons in its surroundings. All right, so the bigger the number is, the stronger the electrons pull. All right, now, there are 3 different types of bonds that we're going to discuss in this class. There's 3 different kinds of bonds. And the type of bond is determined by the difference in electronegativity between the 2 atoms making the bond. All right? So this is the key thing to remember going forward. The difference in electronegativity and just so you know, going forward, this symbol delta, that little triangle, is the capital symbol delta for the Greek alphabet. That means change in. So delta En is change in electronegativity or difference in electronegativity. The difference in electronegativity determines the type of bond between two elements. All right. So what are these types of bonds? Well, there is an ionic bond. All right. That is the first type of bond. We've talked about ionic compounds. It would make sense that they would make ionic bonds. In an ionic bond, electrons are taken, not shared. On the other end of the spectrum, you have covalent bonds. All right, and covalent bonds, as you might suspect, are the types of bonds we find in covalent compounds. And when we talk about covalent bonds, in covalent bonds, electrons are shared evenly between the two atoms, between the two nuclei. And then the third type is something we call polar covalent bonds. I'm gonna just scoot this up. Polar covalent bonds. And in polar covalent bonds, electrons are shared unevenly. And we'll talk about what all of that means. All right. Taken out shared, shared but unevenly, and then shared evenly are the three types. Now, if your bond is polar covalent, the difference in electronegativity will fall in between 0.5 and 2.0. All right, that if it falls between 0.5 and 2.0, including 0.5 or 2.0, so that looks like 20, then the type of bond is a polar covalent bond. If your difference in electronegativity is less than 0.5, then your bond is covalent. If your difference in electronegativity is greater than 2.0, then your bond is ionic. All right? So looking at the electronegativity numbers for two elements that are in a bond and taking their difference is how you determine whether or not the bond between those two elements is ionic, covalent, or polar covalent. Let's do a few examples so we can kind of see how this all works out. All right, so for example, if you wanted to know So if you were asked the following question, is the bond, or let me see, I'm going to say determine if these bonds are ionic polar, or covalent. Yeah, kind of. So determine if these bonds are ionic, polar, or covalent. So let's look at the bond between carbon and hydrogen. All right. The first thing you got to do is you got to look up the electronegativity for carbon and hydrogen. These will be, by the way, provided for you on the exam. I'll tell you what they are in the problem. The electronegativity for carbon is 2.5. The electronegativity for hydrogen is 2.1. So if we take the difference between them, 2.5 minus 2.1 is 4.0. All right, this is, right here, the difference in electronegativity. So that's what we meant by the difference in electronegativity. You literally subtract one from the other. It's always subtract the smaller one from the bigger one. An electronegativity of 0.4 is less than 0.5. That makes this a covalent bond. All right. What about the difference? What about the bond that would form in between fluorine and lithium, for example? Fluorine's electronegativity number, and again, I'll provide these for you, is 4.0. Lithium's electronegativity number is 1.0. So if we take the difference here, 4.0 minus 1.0 is 3.0. So our difference here in electronegativity is 3.0. That is larger than 2.0, right? 3 is bigger than 2. And if your difference in electronegativity, I know, it's kind of awesome, right? The difference here in electronegativity, since it's larger than 2, means that this bond is ionic. All right, looking at one more example. Let's examine the bond formed by oxygen and hydrogen. Oxygen's electronegativity is 3.5. Hydrogen's electronegativity, we've already seen, is 2.1. And so the difference in electronegativity here comes out to be 1.4. Now, 1.4 isn't smaller than 0.5. It's not bigger than 2. It's in between 0.5 and 2. So that means, yeah, and Carolina, I will totally give you the electronegativities for all of these. You just need to know what the difference means. The difference in electronegativity here is in between 0.5 and 2. So that means this is a polar bond. Carolina, great question. So Carolina asked, how do you know which one to subtract? You always subtract the smaller one from the bigger one. Your difference in electronegativity should always come out to be positive. All right. So subtract the small one from the big one. You get a positive difference in electronegativity, and you're good to go. Totally, not too shabby. All right. So that is how you determine what type of bond you're dealing with. Yep, Ariana, that is correct. You always subtract for this situation. All right. Now, so to recap, the critical thing you got to remember is polar bonds are in between 0.5 and 2.0. Ionic bonds are greater than 2.0. Covalent bonds are less than 0.5. All right, that is how you categorize each one. Now, I want to talk for a minute about polar covalent bonds. All right, polar covalent bonds. In polar covalent bonds, the electrons are unevenly shared. All right, they're unevenly shared. That means that they spend the electrons spend more time around the atom with the higher electronegativity. All right, and this has consequences for the molecule's behavior, for molecular behavior. All right. Let's investigate how this affects the structure. So we're going to look at a molecule of HF. We've already done the calculation here for the electronegativity. Fluorine has an electronegativity of 4.0. Hydrogen has an electronegativity of 2.1. Or actually, we haven't done HF yet, but now we are. All right, so our difference in electronegativity here is 1.9. This is squarely in between 0.5 and 2.0, right? It's near the end, but it is definitely a polar bond. All right, and so we got a polar bond, and we know what that means. That means that the electrons like to spend more time around fluorine than they do around hydrogen. All right, the electrons, the two electrons in this bond, spend more time around fluorine because fluorine is pulling harder on them than hydrogen, right? Fluorine's more electronegative. And what that does is it creates an uneven distribution of electrons. They're only at hydrogen's part of the time, they're at fluorine's most of the time. And because electrons are negative and because they spend more time around fluorine, fluorine picks up what we call a partial negative charge. This is not a full-on negative charge. That symbol right here, this guy, that is a lowercase delta, which is the Greek letter for D. And what it means, more importantly, is a partial charge. It's not a full-blown ionic charge, but there's a slight negative charge to the fluorine. Because hydrogen doesn't have the electrons as much as fluorine, they're spending more time around fluorine, hydrogen is left with a slight positive charge, not a full-blown positive charge, but a partial positive charge. So we have partial negative, partial positive, partial positive over here on hydrogen, partial negative over here on fluorine. All right. The uneven distribution of electrons in the HF bond creates an uneven charge distribution in the molecule. So this molecule, even though it's covalent, even though the electrons are shared, has a positive end and a negative end. All right. This is what happened Christmas morning, or maybe Christmas afternoon, 1996. Right. You just opened your brand new Nintendo 64. It was unlike anything you'd ever seen. There'd never been video games in 3 dimensions before this. And now all of a sudden there were. And because your parents didn't know what up, or that games would need more than one controller, there's only one controller in the box, and you're playing Mario Kart, and your little brother is whining for a turn, right? And so what does your mom say? She says, well, share with your little brother. So you don't want to outright disobey her, right? Because you know then you'll probably get banned from the thing forever. So you gotta share with them, but you decide to do it deviously. You decide to say, okay, little brother, for every 3 rounds of Mario Kart I play, I'll let you play 1 round. And that type of sharing is exactly what's going on in this bond. The fluorine is going like, hey, I'll share these electrons with you, but for every 3 rounds I'm playing, you get 1 round. Technically they're shared, but the fluorine has the electrons way more of the time, just like you have the controller to the N64 way more than your little kid sibling did. All right. That is what a polar bond does. That's what a polar bond is. It's unfair. It's an uneven distribution of the one N64 controller. All right. Now, up here, let me add in my partial positive. When you have polar bonds in your molecule, those polar bonds can make your entire molecule polar. All right? Those polar bonds can make your molecule polar, which has implications for has implications for molecular attraction. Sorry, I just saw Carolina's comment and it literally made me laugh out loud, as you saw, because I just laughed out loud. All right. HF is an example of a polar molecule. All right, a polar molecule. And that becomes so polar molecules that are polar, molecules with an uneven distribution of electrons, molecules with polar bonds can themselves become polar, because the thing is, another way you can represent this is with what's called a dipole. This is the negative end. And this is the positive end. Okay, let's see. Yes. So Rox just asked, so for polar bonds, you'll always have a positive and negative end to that tail. And yes, every polar bond will create a positive and a negative end. That is true. And having polar bonds is a requirement for a molecule to be polar, but having polar bonds does not guarantee that the molecule will be polar. So, for example, let's look at a couple molecules for by way of example. All right. So let's talk about molecular attraction. If you look at a molecule of water, and here you'll notice that I'm drawing it with its VSEPR geometry, right? With its bent geometry. And I want to compare this to a molecule of carbon dioxide. We can look at the difference in electronegativity for the bonds in water. Oxygen has an electronegativity of 3.5. Hydrogen is 2.1. That difference comes out to be 1.4. So this is right here. We're dealing with polar bonds. All right, polar bonds in water. Here, sorry, I just got to rearrange my page just a little bit. Whoa. All right, let's look at the electronegativity difference for carbon dioxide. Oxygen has an electronegativity of 3.5. Carbon has an electronegativity of 2.4. So this electronegativity difference is 1.1, and still 1.1 is in between 0.5 and 2. So we're dealing with polar bonds in carbon dioxide. So both of these molecules have polar bonds. All right. Nope. So Carolina, great question. You do not add 2 for the H because you're only looking at the individual pull between one oxygen atom and one hydrogen atom. So it's ever just one on one. One bond is one oxygen with one hydrogen. So you just look at the electronegativity for one oxygen, one hydrogen. The second, so that first bond is polar. The second bond is polar because the difference between oxygen and hydrogen is the same. Same thing with the CO2. You only look at the electronegativity of one atom minus the electronegativity of one other because you're looking at an individual bond. Hopefully that makes sense. All right, both of these bonds in both of these molecules are polar. All right, that creates totally, and great question, by the way. That creates, so for oxygen, oxygen's more electronegative, so it creates a partial minus on oxygen and a partial positive on each hydrogen. For CO2, oxygen's more electronegative, so carbon gets a partial positive and oxygen, I'm actually going to do this in a different color. Carbon's partial positive, oxygen's partial negative. When we draw the little individual dipoles, you can see for oxygen that one of them is going to be slanted up along the bond towards from hydrogen to oxygen, right? Positive at the tail, negative side is at the arrowhead. Same over here. When you look at carbon dioxide, however, positive end is the tail, negative end is the arrowhead. You'll notice here that the bond dipoles are pulling in opposite directions. And this is important, with equal strength which means they cancel. Each other. All right, they cancel each other out. Ah, Brianna, great question. Brianna, the partial negative will always go in the atom with the larger electronegativity number, and the partial positive will always go on the atom with the lower electronegativity number. And on the exams, in the problems that you're doing, I will tell you oxygen's electronegativity is 3.5, hydrogen's is 2.1, or carbon's is 2.4. So I'll explicitly give those to you, and the partial negative is on the one with the higher electronegativity. Partial positive is on the one with the lower electronegativity. Okay. Sorry, Carolina. I just saw your question was the same as Brianna's. So, yeah, totally, totally. You'll notice that with carbon dioxides, the two mini dipoles cancel each other. They're pulling in opposite directions with equal strength. So it's like a tug of war between two people who are equally strong, right? That rope isn't going to move anywhere. But with oxygens, they're not going, if they were going like this, dead on, wait, here we go, dead on, bump, 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 they would cancel each other, but because they're slanted at an incline, they don't cancel each other, and so they are, so we would say that H2O is a polar molecule. Is a polar molecule because dipoles don't cancel. All right, so when you have polar bonds in your molecule, you have the possibility of having a polar molecule, but it does not guarantee that the molecule will be polar, all right? It doesn't guarantee it. Now, if you find yourself wondering, well, how do I know? How will I know if all my dipoles cancel or not? I'm so glad you asked. I'm going to tell you. This ties back into what we learned about VSEPR theory, all right? With VSEPR, our VSEPR electronic metry. All right, we got to look back at our VSEPR electronic geometry. So, first off, if your geometry is linear, that means, let's remember our electron groups. If you're linear, that means you have two electron groups. If you're trigonal planar, you have not four, three electron groups. And if you're tetrahedral, you will be four electron groups. All right. Now listen. When all electron groups around the central atom are the same, dipoles cancel, and the molecule is nonpolar. All right, that's the thing to remember. When all the groups around your central atom are the same, your dipoles cancel, and you're non-polar. That's what we had going on, for example, in our example of CO2. All right, CO2 is linear, which means it has 1, 2 electron groups. And guess what? In this molecule, those 2 electron groups were both oxygens, so they're the same, which means the molecule is nonpolar. That's why they cancel. Now you might be going, well, wait a minute, Josh. In water, oxygen or central atom had 2 hydrogens attached. Why wasn't that nonpolar? Let's take a look. What is water's electronic geometry? You're right, water does have 2 hydrogens, but it also has 2 lone pairs. So we actually have 1, 2, 3, 4 groups around water. Water, the oxygen in water, is tetrahedral. For a tetrahedral molecule to be nonpolar, it would have to have the same group on every one. Since it doesn't, if that oxygen had 4 hydrogens, it would be nonpolar. But because it does not have a hydrogen at each position, since they're not all the same, it's going to be polar. And that's why it's polar. All right, so I'm going to keep this handy. Polar molecules, a molecule needs 2 things to be polar, all right? There are 2 things that qualify a molecule for polarity. Yeah, there we go, tetrahedral. First, you need polar bonds. If your molecule has polar bonds, then it might be polar, but it doesn't guarantee it. In addition to polar bonds, you must have polar bonds, but you also must be asymmetric. All right, your molecule needs to have polar bonds and be asymmetric, i.e., all of its electron groups cannot be the same. All right, at least one of them's got to be different. So let's do a couple examples. Oh wait, no, hang on. So let's do a few examples. is this molecule polar or nonpolar? All right, is this molecule polar or nonpolar? And I will give you the Lewis structure. All right. So here's our electronegativity numbers. Oxygen's electronegativity is 3.5. Don't remember. Oops. There. Okay. Yeah. There we go. Sulfur's is 2.5. So if we find the difference in electronegativity, it's going to be 1.0, which means we have polar bonds. Which is one of the two things we need. Second, we need to make sure that the molecule is not symmetric. So you have to ask yourself, how many electron groups do we have here? Sulfur has no lone pairs and 3 atoms, so it has 3 electron groups. And you'll notice that all 3 electron groups are the same. All 3 are the same, which means that we have a non-polar molecule. All right, non-polar molecule because all 3 are the same. Let's do another trigonal planar example. Polar or non-polar? Let's look at formaldehyde. All right, here we have a few electronegativities to look at. Carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. So when you take their electronegativity difference, it's 0.4. This is nonpolar. So the carbon-hydrogen bonds are nonpolar. Let's take a look at the carbon-oxygen bonds. Oxygen is 3.5. Carbon is 2.5. So the difference in electronegativity between oxygen and carbon is 1.0. That makes the carbon-oxygen bond polar. So we do have a polar bond. This might be a polar molecule. The question is our molecule symmetric or is it asymmetric? When you look at carbon, we have 3 electron groups, right? Hydrogen, hydrogen, and oxygen. Because they are not the same, and there is a polar bond the molecule is polar. All right, that is what that means. All right. Okay, now, why have we been spending so much time talking about polarity? The reason why is this, once we understand polarity, allows us to have a fruitful discussion about molecular attraction. All right, now we can talk about molecular attraction. Rocks, that is exactly correct. Exactly correct. Polar molecules are attracted to other polar molecules and ions. All right, and vice versa. Ions and other polar molecules are attracted to polar molecules. Non-polar molecules are only attracted to other non-polar molecules. So famously, water is a polar molecule. Oil is a non-polar molecule, and that's why they don't mix. If you put oil and water together, there's going to be two different layers, the oil and the water. They're not mixing because water is polar and it's only attracted to other polar molecules and ions, whereas oil, being nonpolar, can only dissolve other nonpolar things. This whole sort of like dissolves like scenario. All right, so molecular attraction and what can dissolve what is determined by that intermolecular attraction. All right. There's one special type of molecular attraction that I want to talk about, and that is a hydrogen bond. Now, hydrogen bonding is a special type of molecular attraction that happens when you have a polar bond between a hydrogen atom and a nitrogen, oxygen, or fluorine. All right. If in your molecule you have a bond between hydrogen and either a nitrogen, an oxygen, or a fluorine, you will get this special type of molecular attraction known as hydrogen bonding. All right. So while second, sorry. Okay, there we go. Sorry, my computer froze. Water is the most famous hydrogen bonder, and here's how hydrogen bonding works in water. So it happens between two water molecules. And as we know, we have a partial negative on our oxygens, right? And partial positives on all of our hydrogens. All right. So partial negatives, partial positives. The partial positive on hydrogen attracts the partial negative on oxygen, right? Because opposite charges pull each other together. And what happens is the negatively charged electrons on one oxygen reach out towards the partial positive charge on the other hydrogen. So they start reaching out, and they almost form a bond with that hydrogen. All right? This is right here a representation of the hydrogen bond. They're reaching out, they almost form a bond, but they're not quite going to form a full bond to that hydrogen. But they're attracted to each other. They're kind of stick together for a little bit loosely. This is something that we've all seen before. Basically, this hydrogen appreciates the attention it's getting from this oxygen. It enjoys that attention. And this oxygen wants to make a bond with that hydrogen. It wants to be in a relationship with that hydrogen. The problem is this hydrogen is already in a bond with another oxygen. It's already in a committed relationship. It's not going to leave that relationship. So it's not going to make a bond with this new oxygen, but it appreciates the attention that it's getting. And so it lets this other oxygen kind of do significant other things for it. It likes it. Hydrogen likes when oxygen acts like its significant other, but it's not actually going to leave its first oxygen and commit to a relationship with the new one. So essentially, the way to think about hydrogen bonding is hydrogen bonding is just teasing. It's molecular teasing, but it's a very strong attraction. It's a very strong, powerful attractive force, just like it is between humans. All right, so this is the molecule that provides the H. This is called the hydrogen bond donor. And the molecule that has the lone pair, this is called the hydrogen bond acceptor. Yeah, totally. That's exactly what it is. And it wants to be more than the side, but that's all the hydrogen's going to let that oxygen be, just its thing on the side. It's sad. It's sad to be a hydrogen bond acceptor. But anyways, that's hydrogen bonding, and now you'll never forget it. Okay, that is the official end of chapter 4. So we still have about 10-ish. We got closer to 15 minutes left in lecture. We're going to just dip our toe into chapter 5, and we'll continue with lecturing chapter 5 on Tuesday next week. Now, chapter 5 is all about chemical reactions. We're going to learn a lot in this chapter. It's another long chapter. And it begins with a discussion of chemical equations. All right. So chemical equations. Just a few things to lay out. So So for example, we're going to start with the combustion of hydrogen gas. So this is the explosion that destroyed the Hindenburg. So this is how you write a chemical equation. I'm going to break down all the parts. So I'm just going to lower this a little bit. There we go. So you'll notice that there is an arrow right here. This is called the reaction arrow. By the way, I don't know if you've seen me write RXN. This is a shorthand for reaction. All right, and I'm going to use that from here on out. So this is a reaction arrow. And the reaction arrow right here divides our chemical equation into two halves. All right. To the left, you have the products. Sorry, that's my dyslexia at work. You have the reactants. And to the right, you have the products, which I'm going to write as PDTS from here on out. All right, so you've got the reactants in your chemical reaction, reaction arrow, products. Reactants are what you start with at the beginning of the reaction. The products are what those reactants turn into as they move from the beginning to the end of the reaction. There's one last thing here that I have not elaborated on. You'll notice these parentheses and subscripted symbols right here. These are called phase symbols. And they tell you the phase of matter that each individual reactant or product is in, all right? G is the gas phase. L is liquid. S, so that looks a little like a G. There we go. S is the solid phase. And AQ is the aqueous phase. All right, and just so you know, aqueous means dissolved in water. All right, the aqueous phase, if something's in the aqueous phase, that just means that that compound has been dissolved in water. All right, so that is the anatomy. That's kind of the breakdown for chemical equations. The deal is, as written, and I just blanked it out. Let me rewrite this. As written right now, there's something wrong with this chemical equation. All right, and what's wrong is, also here, before I say what's wrong, in any chemical reaction, matter cannot be created or destroyed. All right, it just changes forms, but matter isn't created, matter isn't destroyed. It's taken from one form and converted to another. It's for any, I almost said My Hero Academia, sorry, wrong anime. Full Metal Alchemist fans, it's the law of equivalent exchange, right? Everything costs something. If you're gonna make something, you gotta give something, right? You gotta give something if you want to receive. You gotta put something in to get something out. Matter is not created or destroyed. It only changes form. And if you look at this reaction, on the reactant side, you have both hydrogens and oxygens. And on the product side, you have both hydrogens and oxygens. But look at the individual atom counts. There are 2 hydrogens and 2 oxygens on the reactant side. On the product side, there are 2 hydrogens and only 1 oxygen. All right, that is what's wrong with this equation. Matter cannot be created or destroyed, but as written in this moment in time, there is only, you start with 2 oxygens, you end with 1. Where did the other one go? It can't just disappear. There's a name for this type of chemical equation, and we say that this is an unbalanced chemical equation. In this class, in every chemistry class, any chemistry class, you're never allowed to use unbalanced chemical equations because they violate the law of mass conservation, that matter is not created or destroyed. So it is up to you, and it is up to me, to balance these reactions, to balance these equations, to make sure that the number of atoms on the reactant side is equal to the number of atoms on the product side. Now, how can we do that? There's one cardinal rule. You are never allowed... Yeah, totally. It is a mistake. Caroline, it actually is a mistake. It's a mistake we have to correct. You're never allowed to change the subscript of any element in any atom. And the reason why is if you change the subscript, you actually change the equation. You might look at this and think like, oh, well, why don't we just throw a 2 right there? The reason why you can't is because that's a different reaction. H2O2 is hydrogen peroxide. All right, H2O2 is hydrogen peroxide. A reaction where H2 and O2 make hydrogen peroxide is not the reaction where H2 and O2 are making water. So you never touch the subscripts, ever. You can only alter what are called the stoichiometric coefficients, the numbers that come out in front of a number. Right now, as written, you never write the number 1 explicitly in front of a number. It's always just there implicitly. But these we can change. All right, we can change the number of molecules represented in the equation. So, for example, if we wanted to balance this, you'll notice that we have 2 oxygens on the reactant side, but only 1 on the product side. If we want to have 2 oxygens on the product side, that means we need 2 molecules of water on the product side. You'll notice it doesn't change it. It's still H2O. We've just added a second one. When you do this, you change your oxygen count, but you also alter your hydrogen count. Now that we have 2 water molecules, we have a total of 2 oxygens on the product side. But now that we have 2 water molecules, we have 2 times 2, right? 2 times 2 hydrogen atoms. So now we have a total of 4. You'll notice we have balanced our oxygen, but we've unbalanced our hydrogen, right? We've robbed Peter to pay Paul. We've fixed one problem, but created another problem. That is often the way it goes when it comes to balancing chemical equations. This is totally normal. Don't let it stress you. Let's bounce back to the reactant side and see what we can see. So right now, we have 4 hydrogens on the product side, only 2 on the reactant side. We need a balance, so we can add a second molecule of hydrogen. Now we have 2 times 2, or 4 hydrogens on the reactant side. And now you'll notice that our chemical equation is balanced. We have the same number of hydrogen and oxygen on both sides of this reaction. So this is our balanced chemical equation. All right? Let's do a couple more. And we'll continue. We'll have a lot more practice balancing chemical equations on Tuesday, but we're going to knock out a few more examples before, or maybe one more. Let's balance the following chemical equation. One in which solid sodium reacts with aqueous hydrochloric acid to produce hydrogen gas and aqueous sodium chloride. All right. Whenever I'm doing a problem like this, I always take a chemical inventory. I write out each type of atom on both sides of this equation, and I count up how many of each there are. There are some people who can look at a chemical equation and just start throwing numbers and balancing it. I'm not gifted like that, so if you can, totally more power to you, but I've always got to take the slow and steady method. So on my reactant side, I have one atom of sodium, one atom of hydrogen, one atom of chlorine. On my product side, I also have one atom of sodium, two atoms of hydrogen, one atom of chlorine. Now, everything looks balanced here except for hydrogen. I have two on my product side, one on my reactant side. The only way I can get two hydrogen on my reactant side is if I multiply HCl by 2. When I do this, I change both my hydrogen and my chlorine count. So now I have 2 hydrogen on the reactant side, but I also have 2 chlorine. I fixed something, I balanced H, but I've unbalanced Cl in the process. So let's go back to the product side. The only way to get 2 chlorines on the product side is to multiply sodium chloride NaCl by 2. In doing so, I change both my chlorine count and my sodium count. Now I have 2 chlorine and 2 sodium on the product's side. Now I have to go back to the reactant side and fix sodium. Fortunately for me, sodium is all by itself, so if I multiply sodium by 2, it doesn't affect anything other than sodium, and now I have my balanced chemical equation with 2 sodium, 2 hydrogen, and 2 chlorine atoms on both sides of this reaction. All right, I'm going to leave you with an example, and we'll pick up with lecture on Tuesday with this example. So check it out when you, so try it over the weekend, come back, watch the lecture, see if you got it right. So write a balanced chemical equation for the reaction between nitrogen gas and hydrogen gas that produces nitrogen trihydride, or as it's commonly known, ammonia gas. Yep, they sure do. Okay, so go ahead and give this a crack over the weekend, and we'll pick up here on Tuesday. I'm gonna run because I gotta go start setting up for the oral exams. But have a good weekend. I'll catch you in a bit. Oh nope. Is next week spring break? If it's not spring break, we totally have lab. If if we have class next week, we totally are having lab. Um, I don't know when our spring break is. I'm teaching 3 different colleges. Each one is taking a different spring break, so I need to check our syllabus. I'll post more about lab a little later. All right, dudes, I got to bounce.